Others too. Chime up. Go ahead, Adrian.
Number 17 for 20.
Okay. From the homework or from the practice? Well, we'll just read out the question out loud.
Well, it's kind of hard to read. Well, it's silver, solid, and then line, and it's going to silver ion, and saturated. Silver.
We'll come back to that one then. I'm going to bring it up. Somebody else have a simpler question?
You still can do extra credit for the ones who might be.
Oh, right. I need to do that. You could, if you want to do that, you could look at maybe just pick something out of the literature regarding chiral molecules, and you could maybe pick one, biologically significant chiral molecule, and just write a little blurb about that. It doesn't have to be very deep. For the people who couldn't make the extra credit seminar, unfortunately you can't get double extra credit, just one or the other. And so just find a biologically significant chiral molecule and say, at least. All right, so other questions? How about from the practice test? Other questions from the practice test? Well, today what we're talking about is nuclear chem, chapter 25. Although there's one thing that you should know from chapter 14 that I really didn't talk about, and I'm not really going to give examples, but it's the difference between labile complexes and inert complexes. Labile complexes, L-A-B-I-L-E, have ligands that can easily break off and reattach. And so the ligands are constantly breaking off and reattaching. Whereas inert complexes, the ligands are just solidly fixed on there. And they don't really break off. And so something like, O2 on hemoglobin, that would be a pretty maybe labile complex, versus carbon monoxide on hemoglobin would be a more inert complex, more difficult to break off. And so those are terms you might hear in relation, and those are talked about at the end of the chapter. All right, so let's take a look at this number 17. So the silver ion. This is an example of a concentration cell, right? This is a concentration cell generating 0.177 volt. Calculate the KSP for silver chromate. And so what you get is, from the voltage is what? By knowing the voltage, you can determine the difference between the concentration in the anode beaker and the concentration in the cathode beaker. And so over in the cathode beaker, we have 0.125 molar. It means in the anode on the left side, you're going to have less than that, and the electrons are going to flow to the voltage of 0.177 volt. And so what we do here, and what is the question specifically for this one?
I wasn't sure, because silver is being reduced or is being oxidized.
It's a tug of war. Silver is the same strength, right? But if you have more of them on one side versus another, then the side with more wins the tug of war. And so if you have, you know, they're all equal strength, but if you have 10 on one side and 5 on the other, then obviously the side with 10 will win, right? This is the whole concept behind a concentration cell. So how many people got this problem? Just one person? Good, well, good job, Angel. But this is just, I thought this was a pretty basic question, at least for figuring out the silver ion. And then you have to remember about KSP, which a lot of people were asking me about. You know, the two, why did I multiply 2 times the silver ion? Because I multiplied 2 times the silver ion concentration because of its silver chromate. You know, the 2 silver ions for every chromate. And so, what about getting the concentration? Is that an issue there? I mean, or can you visualize a concentration cell? If the electrons are flowing left to right, what does that tell you about the silver? We got silver ions here. We got silver ions here. Electrons are flowing left to right with 0.177 volts. What does this tell you? The right side is more concentrated. We've just got more silver. We can use the Nernst equation to figure out the concentrations, right? Because we already know the concentration on the right side. What is the concentration? 1.125 molar. And so this problem here should be a basic problem for Nernst equation. You know, E of the cell is equal to E naught of the cell. You know, minus 0.0592 volts over n log Q. This is easy because E naught of the cell is 0 volts. Right? So this is minus 0.0592 volts. N? 1. Q is products over reactants. The silver ions here, is that product or reactant? Reactant. And so that goes down here. You know, the concentration is 0.125. And up here, we don't know what the concentration is, so that's our X. This is all for X. Since we're getting close to the end of the chapter, you know, this is good to refresh your memory about what KSP is. So we solve for X, we get the silver ion concentration on the left. Once we get the silver ion concentration, then, you know, the KSP equation, which surprisingly a lot of people got wrong, because they wrote it backwards. You know, they wrote silver ions plus chromate goes to silver chromate. That's wrong. It's solid silver chromate goes to silver ions. 0, 0, plus 2s, plus s. This is why I multiplied by 2. Some people were asking me that about the key. Why did I multiply by 2? I multiplied by 2 because of this coefficient. But, you know, when I redo this, I'm not solving for 2s. 2s is a silver ion concentration. I'm solving for s. S is the solubility of silver chromate. Just so happens the 2s comes because of the silver ion concentration, because this silver ion concentration, right, is equal to 2s. Okay. All right, that's this basic setup for that problem. Okay, other questions? Well, how about Matthew? I have a question for you. Number 18, how many electrons are transferred in this? Let's see if this is a good test. So number 18, how many electrons are transferred? reaction. What did you get? 8? Oh. Both. All right. Yeah, you're right. The first one, the true number 18, because this one's a typo. This one should be 19. So this is a typo. Yeah, you got it too. What is it?
Goes from -4 to +4.
-4 to +4, which is 8. And so the answer is 8. Or you could just do the oxygens. You have 4 oxygen atoms. Each oxygen gains 2. 2 times 4 is 8. You know, either way, you look at a reducer or oxidizer. This one, I'd say maybe about 10 to 15% of the people got the N wrong on that. What is N? This one's a lot easier. Here, for sure.
Will we have the redox chart? What is it going to take?
Will you have a redox chart? Yes, you will have the redox chart. Not that one, but the one from the book. Uh-huh. Number 9? Number 9 is false, right? If you have a very low concentration of solutions, your battery's not going to last very long. You know, it's not a very good battery because you want lots of reactant for a long-lasting battery. Okay, what else? 16. Yeah, doubles. Okay, you double that. What's that going to change? Yeah, well, let's look at A, E cell. No, you make it last twice as long. Rather than having a pound of zinc, you have 2 pounds of zinc, right? 2 pounds of zinc is going to last a lot longer than 1 pound of zinc. E not of the cell. No. Delta G. Yes, if you double it, then you're going to get twice as much energy, because if you have 2 pounds of zinc, you should yield twice as much energy. Delta G naught.
No, it's that's the standard.
Yeah. Delta G naught, this is very tricky because delta G naught is, yeah, 1 bar, 1 molar, right? So it's under standard conditions. So let's say 1 pound of zinc yields 400 kilojoules of energy under standard conditions, 1 bar, 1 molar. What would, how many pounds did I say? 1 pound. What would 2 pounds yield? The same exact energy, just because you're doing it at 1 bar, and it would double, right? It would double. Right. Energies like this are extensive. All energy quantities are extensive properties. Do you guys remember extensive versus intensive back in chapter 1 of Chem 1A? And so C and D are gonna double. Delta H, double. Delta H naught, delta S, delta S naught, double. But voltage is an intensive property. Voltage is going to depend on the concentrations, because what you're doing is you're taking energy over N, the moles, right? You see, you're normalizing it here. So if you have 50 moles of electrons transferred, well, you're dividing by 50. Those per mole, right, of electrons. And so E to the cell and E not to the cell don't change. Only if you do what? Change the concentration, which wasn't specified, so you can't assume. Okay, what else? circle all suitable cathodes. What's happening at the cathode? What's a cathode half reaction? Yeah, what is it specifically?
CO2 plus 2 electrons.
Yeah, so you just need something to feed electrons to Cu2 plus that won't react with Cu2 plus. So I asked you, what were all the things that react with Cu2 plus? Remember that question I gave? In the lab? Yeah, I looked through those, and I think a lot of people need some more work with chemical reactions. But so you figure out, will zinc react with Cu2 plus? Yes. Will copper react with Cu2 plus? No. Platinum? Magnesium? Graphite? No. So you got it. That's good. It also has to conduct electricity. If it doesn't conduct, it's not going to be a suitable cathode.
So BCD would be the answer because they
Yes. BCDs. All right. Any others? If something comes up, you can ask me. I'm sorry? For 12, for the reaction, circle all suitable anodes. Only A.
Wait, how do we basically
Only A.
why is it
Yeah. Otherwise, you can't get that reaction. It's impossible. So zinc has to be in. Okay, anything else? No. All right, let's take a look at chapter 25. Like I said yesterday about chapter 25, it's a pretty long chapter. You know, if you look at the sections, radioactivity, naturally occurring, radioactive isotopes, nuclear reactions, etc. So we're going to just do a survey of this chapter. It being a survey, the stuff I'm going to test you on is only the stuff I talk about. You don't have to read everything in the chapter to deal with this. So let's take a look at radiation first. Radiation was discussed in chapter 2. Do you guys remember it? In chapter 2. Yeah. What types of radiation? You have two major types, particle radiation and electromagnetic radiation. Right? The particle radiation, you have alpha particles, beta, gamma. Gamma, are those particles? No. Gamma is electromagnetic radiation. Electromagnetic radiation, alpha particles and beta particles can be deflected by magnetic fields, right? But light, will it be deflected by magnetic fields? No. So that's one way we see, or electric fields, don't matter. But what's the origin of this radiation? Actually there's different origins of radiation. So for example, to make X-rays, there are different ways you can make X-rays. One way we used to use to make X-rays is use copper in very high voltage, knock electrons off of it, and then up from low energy orbitals and electrons for higher energy orbitals drop down and start emitting X-rays. So you crank up the voltage on this and you can generate X-rays. But X-rays can also be generated from, or they just naturally occur from, radioactive isotopes, right? Radioactive atoms. And so when we look at radioactive, well, what does radioactive mean? Radioactive just means it's unstable. And the way it typically decays into something more stable is by emitting radiation. And so we are looking at radioactive atoms. Sometimes we call these isotopes, radioactive isotopes, or if you're looking at an individual isotope, we call it a nuclid. An individual isotope. In other words, one atom of one isotope is a nuclid. And so we have something, an unstable atom here. This is unstable. And what makes it unstable? Is it the electrons? The electrons are in some excited state? No. No, it's not the electrons. In fact, nuclear chemists don't really concern themselves with valence, core, those things. Nuclear chemists look at the nuclei. And so what we have is we have an unstable nucleus here. And, well, it's not going to stay unstable forever, right? It's going to decay into something more stable. Right? We call that radioactive decay. And in this decay process, right, it'll emit radiation. You know, it's got to emit some kind of energy, so that energy is going to be in the form of radiation. When we look at the radiation, let's look at the radiation in terms of the two types, the particle radiation. For particle, there are two particle, well actually more, we could have neutrons being emitted too. And so let's look at the particles. For example, we could have alpha particles. Alpha particles, are they radioactive themselves? An alpha particle is at He, 2 plus. This is 2,4. Remember 2,4? Something like that. What's 2,4? And this is, we call this helium-4 2 plus, right? Helium-4 is the isotope. But what is it? An alpha particle is the nucleus of the helium atom. And so what happens is, well, what is the nucleus of the helium atom? The nucleus of the helium atom consists of 2 protons and 2 neutrons. Cluster. And so when an alpha particle is emitted, a chunk of the nucleus breaks off. The chunk of the nucleus is 2 protons and 2 neutrons as a cluster. That 2 protons and 2 neutrons is essentially equivalent to a helium nuclei. Nucleus. That's it. Are alpha particles radioactive? No, alpha particles are not radioactive. The nucleus of a helium atom is incredibly stable. But this is the most dangerous form, or one of the most dangerous forms of radiation because of, not because it's radioactive, because of its right. Because of its what we call that, because of its reduction or oxidation potential. Yeah, it's incredibly high. Oh, wow, okay. this is the usual. You get both answers. Which one's correct? You'll have to arm wrestle for the right answer. No, is it oxidation? Incredibly high oxidation potential? It's a very powerful oxidizing agent, which means it's got a very high oxidation potential. That's typically what you'd think. Very high, very strong oxidizing agent. No, actually it's backwards. It's a reduction potential. And so it has extremely high reduction potential, much higher than, it's off the charts high. Right? This is very reactive. This stuff wants what? Electrons, and so it's a gas. So what happens is people inhale it. When they inhale it, it takes electrons from your lungs and whatever else it comes in contact with. That's a problem. It can take electrons off your skin because your skin is beat from sun, general exposure to radiation. You know. And so your skin has repair enzymes that go and fix the damage. Like this was a long time ago when I was taking biochemistry. You know, I should look up the new value. It's probably easy to find, but I haven't. But this is a number I always remember because when I was taking biochemistry, you know, they said that your DNA is cleaved 200 times a day. You know, the bond is broken. And then the repair enzymes come and fix it, right? And so even though it could cause a lot of mutations, it doesn't because the repair enzymes fix the damage that's caused. Nowadays, it must be much higher than 200 times a day because of the ozone depletion. But your lungs, do they have repair enzymes to fix damage from? No, and so that's the problem. And so this is very damaging radiation. You know, as far as radiation goes, we have different ways we express radiation. So let's talk about the different ways we express radiation. This is why I say I'm not going in order of the book. We look at the effect of radiation on matter. Well, the effect of alpha particles are they have a huge reduction potential. They're going to cause damage. When things can strip electrons, it can form ions, and we call it ionizing radiation. Ionizing radiation. So alpha particles are ionizing radiation. They can form ions easily. Well, when we're talking about exposure, radiation exposure, let's look at the different ways we can express radiation exposure. You know, one way we could express it in terms of becquerels or curies. You know, becquerel or curie is, you know, how many of these particles per second, you know, disintegrations per second. How many particles per second? The particles per second would be any ionizing radiation that causes a signal. And so a particle or disintegration per second could be an X-ray. X-rays can be ionizing to certain things. A gamma ray, a beta, or a alpha particle. And so if you have, let's say, 1,000 becquerels, then you have 1,000, you know, per second, right, of those. But what would you rather be exposed to? You know, if you had a choice, you know, let's say 1,000 becquerels of X radiation or 1,000 becquerels of gamma radiation. For sure, X radiation. Why? It's less damaging. You know, gamma rays are much higher in energy, right? And so, you know, this isn't the greatest. Well, you know, because I used to work with radiation, I would have to wear a radiation badge. Radiation badge, you know, it's a piece of film stuck in plastic, and every month you turn in your badge, and then they analyze it to see how much radiation you've been exposed to. And if you've been exposed to too much radiation for that month, you have to take a break from it, so you don't exceed the maximum, you know, dosage that they've set. But I always thought that was kind of ridiculous, because here you could be sitting, working away, and being exposed to huge amounts of radiation, not know it until a month later when you get your results back. It's not the best feeling. But it's pretty controlled, because there's only one source of radiation, and not so bad. But if it were unknown, then that's not the most comfortable. You want something real time to tell you to get out of there. Right, but then again, you don't know what the radiation is. Is it gamma rays? Is it beta? Is it alpha? Right. So we have this thing, the rad. A rad or a gray. 1 gray of radiation deposits 1 joule of energy per kilogram of matter. And so this is a little better, because if you had 1,000 becquerels of X-rays versus 1,000 becquerels of gamma, which one's going to give you more damage? The gamma. The gamma is much more energetic. And so if you're looking at 1,000 becquerels of each of those, then the number of rads will be totally different. The rads, because even though it's 1,000 becquerels the same, the rads that you get from gamma radiation versus the rads you get from X-rays will be significantly different. For X-rays, you just use lead, lead sheets. You probably go to the dentist's office, use lead, right? Or for gamma, for protection from gamma, you don't use lead sheets. You use lead bricks. These heavy lead bricks that you arrange to protect yourself from gamma radiation. And so gamma rays are much more penetrating than X-rays, and when they hit, they're going to excite electrons and ionize things, right? And so a rad is better than that. But the same thing happens, You could have been dosed with 1,000 rads. Okay, I got 1,000 rads of red light versus 1,000 rads of gamma radiation. So it's 1,000 rads of radiation exposure, right? And so that's just 1,000 joules per kilogram. That's a lot. But 1,000 joules per kilogram, right? Of red light versus 1,000 joules per kilogram of gamma radiation. So it's 1,000 rads, 1,000 rads. Does it sound? No, it doesn't sound the same. So that's not good. And so the people who use these always work with the same kind of radiation. If you work with the same kind of radiation, then you know how significant it is. But if you're working with different sources of radiation, then you got to be careful, right? And so what's better is this, a REM. A REM is much better, because a REM or a sievert is it's the biological impact of that radiation. And so what you do is you take the rad and multiply it by some factor. And so, for example, red light, does that have much biological impact? No. Red light is going to cause nothing, right, as far as damage goes. And so if you have 1,000 rads of red, you'd multiply it by some Q factor, and that would lessen its REMs, right? Whereas if you have 1,000 rads of gamma radiation, then the Q factor is going to be bigger, right? It'll be more significant. And so what is the Q factor for different types of radiation? Well, the Q factor for X-rays is 1. Yeah, Q factor for X-rays is 1. So that means red light must have a Q factor much less than 1. Right. But look at this. Q is about 1 for X-rays and gamma rays. So gamma rays are a little more energetic, right? And beta particles. Q factor is 3 for slow neutrons. Q factor is 10 for protons and fast neutrons. And Q factor is 20 for alpha particles. So alpha particles are quite dangerous. Which brings up, an alpha emitter that's present in certain communities. Communities that have granite in the soil. A lot of granites have uranium as a impurity, and the uranium will decay and emit alpha particles. And so these places that have decomposed granite, on the soil or whatever, surface layer, tend to have radon gas as a problem. And radon gas can collect in poorly ventilated areas. And people can inhale radon, which is an alpha emitter, and causes damage. And so up in Palos Verdes, there's been a lot, even the elementary schools there, they measured significant quantities of radon gas, right? And so they made some changes, increase the ventilation, that kind of stuff, cut it down. Depends on the soil, the makeup of the soil. And so alpha particles, you got to, of course, watch out for. But alpha particles are very easy to protect yourself. Since they have very high reduction potential, they pretty much can oxidize anything. And so if you have a piece of paper will shield you from alpha particles, right? As alpha particles are just going to oxidize the paper rather than whatever else. And so a piece of paper is enough to shield alpha particles. Beta particles, you need a little bit more. You know what beta particles are? Beta particles are electrons. These are funny. Electrons. Well, that sounds like chemistry. The electron gets knocked out from either the valence shell or the core. And so why don't we just call them electrons? Like electron gun or something like that. Electron beam. You don't have a beam of electrons. But these are funny electrons because these electrons don't originate from the valence or core. Do you know where these electrons originate from? These electrons originate from the nucleus. And so how can you get electrons from the nucleus? There are no electrons in the nucleus, right? They originate from the nucleus via some kind of decay process, which we'll talk about a little bit today. And so electrons originate from the nucleus. Those are beta particles. This is a particle. So alpha particles are positively charged, beta particles are negatively charged. We can also have neutrons emitted. Neutrons are quite damaging, you can see. You see this? 3 for slow neutrons, 20 for fast neutrons. Oh, 10, sorry, 10 for fast neutrons. And so 3 neutrons. And neutrons have what charge? 0. 0 charge. Because of their 0 charge, neutrons are very dangerous. Why? Neutrons are very dangerous. If you got hit by an alpha particle, would you yourself become radioactive? Or yes? If you got hit by alpha particles, would you become radioactive? No. No. You're going to have sustained damage, right? You get hit enough. Actually, there's this one. I started watching this documentary on Netflix about, because did you hear about the polonium, tea, or all these spy things that were happening, or Russian KGB agents or something like that? Well, there's a journalist who died not too long ago, right, from polonium poisoning. And then there's that The guy in England, there's a documentary that died, right? The spy. Oh, anyway, they ingested polonium, and the polonium is a alpha particle emitter, and it just caused too much damage, right, to their body. Their body couldn't repair all that damage. They ended up dying, but they couldn't get rid of it, right? How do you get rid of the polonium out of your body? They tried lots of different things, I'm sure. You know, polonium's a heavy metal. Maybe they tried a chelating agent. What would be a chelating agent? You might try to get rid of it. Heavy metal poisoning. EA is the correct first and last. EDTA, you know, other things like that. I'm sure they tried that or something else. But unfortunately, they couldn't get rid of it, and so it caused too much damage. And then beta, would beta, getting hit by beta radiation cause you to start glowing or become radioactive? Well, maybe if you get some electron transitions and you get some fluorescence or something like that. But beta is probably not going to make you radioactive, right? No. If you get hit by neutrons, getting hit by neutrons might make you radioactive. Why? Because the neutrons, yeah, will make what unstable? Yeah, you know what happens with neutrons? Even with slow neutrons. Do you guys remember the Rutherford scattering experiment? Chapter 2? The gold foil experiment? What did he do? He shot alpha particles at gold foil. Most of them passed through. Some of them completely bounced off. The ones that bounced off, what did they hit? The nucleus. So alpha particles are positively charged. Nuclei are positively charged. So you get huge electrical repulsions causing it to bounce off, right? But if you shot neutrons at gold foil, what would you see? A lot would go through, but a lot wouldn't bounce off. Why wouldn't they bounce off? There's no repulsion. What happens is they go in, hit the nucleus, and stick. And there's nothing repelling neutrons from the nucleus. So the nucleus, even a slow, what we call thermal neutron, a slow room temperature neutron, can easily get into the nucleus and stick. When it sticks in the nucleus, what happens is you create an unstable nucleus or isotope, which makes it radioactive. And so a lot of people who work with neutrons, what they end up having to do, like neutrons are useful because X-rays, when you use, I used to use X-rays to look at crystal structures. And hydrogen atoms are almost invisible to X-rays. In fact, they're pretty much invisible to X-rays because X-rays like to interact with electrons, and hydrogen atoms only have one electron. And so you don't really see them. The way you can pinpoint where the hydrogen atoms are in 3D space is by using neutron diffraction and hitting it with neutrons. And so, well, you have to go to places like Stony Brook in New York where they generate neutrons, and then you bring your sample there and then you can pinpoint the hydrogens, which is important for some things. When people do X-ray structures, they just say, okay, hydrogen is going to be 1 angstrom off of this, and then they can just calculate where it should be, But anyway, I was reading that, when they're doing this, they have to replace all the steel. All the steel gets exposed to too many neutrons, and they have to replace it after a while because it starts getting really brittle and starts to decay. It's stainless steel and other alloys. Things start to turn. And then there was a whole idea of the neutron bomb. Did you hear about the neutron bomb? The neutron bomb, because you think, neutrons, neutron's going to damage neutrons might make the buildings a little radioactive, but neutrons kill living things? Yeah. And so the whole idea behind the neutron bomb was to leave the infrastructure intact and just kill the living things. But neutrons are very dangerous, right? neutrons. And so 10 for fast neutrons and 3 for slow neutrons. So it shows you the impact compared to X-rays and gamma rays. So we have things like neutrons, you know, and then these are neutral. Then we have protons, you know. Protons obviously can. So you know, these are the particle forms of particle radiation that you might see from radioactive nuclei. As far as electromagnetic radiation, right? EM radiation, what types of radiation do you see? And so if we look at electromagnetic radiation, then there's just two that we concern ourselves with. The first one would be X-rays, and the second one, gamma rays. And usually what happens is electrons, you know, electrons get excited to some very high energy state and drop down to some very low energy state, and they emit X-rays or gamma rays. How do these electrons get excited? They get excited during the decay process. You know, lots of energy is involved. And what can happen is it can knock a core electron out of there, right? And then one of these electrons falls down. In fact, this is used. This is used for something called X-ray photoelectron spectroscopy. You know, it's something they took up on the moon. They took up on the moon. They wanted to figure out what is the elemental composition of this rock, right? You know, what atoms are in that rock. Well, how do you figure out what atoms are present in a rock? Well, you do chemical analysis. Well, how do you do chemical analysis on the moon? How many options do you have? Not a whole lot. And so one of the options is this. They blast photons at the rock to knock the core electron out of there. You knock a core electron out, the valence one comes back in, and then X-rays are emitted. And what you do get is an X-ray spectrum. And the X-ray spectrum is characteristic of the element. And so you can identify the elements. Have you seen this before? Yes, you saw it in what chapter? Chapter, was it chapter 8? Yeah, quantum. Actually, I forgot which. Let's see if this circuit. Here it is. And so, yeah, this is kind of the same process here. Copper emits these lines here. Actually, this is what we can use. You know, we have different names for these lines. So we use the copper K alpha line for looking at crystals. And then you have so you can get the elemental composition by looking at the spectrum, and you can see each one has a unique fingerprint. You know, it's different than the others, right? Because they all have the orbitals, different energies. All right, so now we talk. Okay, we have a radioactive nuclid. You know, what makes the nucleus unstable? You know, and so let's look at the stability of the nucleus next. If we're looking at the stability of the nucleus, what do we want to know? You know, well, our approach is the same. You know, the scientific approach to this. But let me tell you, nuclear chemists and chemists deal with different set of rules. Chemists deal with quantum. Quantum is based on what? If you were to sum up quantum, you know, somebody would ask you, yeah, what exactly is quantum mechanics, and what would you tell them? You know, in simple terms. What exactly is quantum mechanics? A lot of people say, oh yeah, behavior of tiny things, but you know, these tiny things, it just doesn't quite click there. Somebody give me a good, simple, easy to understand blurb of what is quantum mechanics? Well,
The character of nature is quantized. The composition.
yeah, but you know that's like a postulate. Okay, take this without proof or anything. You know, nature is you know, energy is quantized, right? There's certain postulates in quantum mechanics you just got to take without proof. Yeah, but we could do maybe we could do a little bit better than that. You know. This is why I think it's so important. It's so important to, if you, and obviously you don't have the time to do this for everything, but for certain things, like you want to do this, you want to kind of summarize it in your own words or come up with some kind of mental picture of what exactly it is so that it makes it easier to remember. You know, if you just memorize somebody else's words, you know, then yeah, maybe you'll remember it, maybe not. But it's much more significant if you can just summarize what quantum mechanics is in your own words. What is it? Well, we've been doing this since Chem 1A. What do we look at when we look at chemistry? You know, what's the most important thing we look at in chemistry, chemical reactions, this kind of stuff? Hmm? Interaction between positive and negative, right? But that's simple. You know, you can simplify it into point charges. You got positive charge here, negative charge here. So we've been doing a point charge. We look at lattice energies, that type of stuff based on kind of a point charge picture of it. But we need to be a little bit more sophisticated than just say like charges repel, opposite charges attract, because when we look at the charge, how the charge is distributed in atoms and molecules, what tells us how the distribution of charge is? The electron cloud. Where do the electron clouds come from? Quantum mechanics. So all quantum mechanics is looking at the electrical interaction, right? In a lot more detail than just simple positive and negative balls being attracted to each other, right? Or point charges. And then, you know, there's wave mechanics inserted, like, you know, de Broglie. Matter has wave properties too. The whole concept of the electron. But basically, quantum mechanics is just trying to tell us, you know, because what are these electrostatic map? Why do we even care about electrostatic map? Why did I ask you to write down all the charges on the acid, Spartan acid lab? You know? Why is all that important? Why is that all important? Because that's chemistry, right? Figuring out the charge densities, figuring out how the negative and the positive interact, right? And so, well, nuclear chemists don't care. In fact, nuclear chemists don't write alpha particles like this. They write alpha particles like that because they can care less about the 2+ charge or no 2+ or 2+ charge, right? They could care less about that. Why? Because the nuclear chemists, they don't really care about electrical interactions. They care about nuclear forces, nuclear interactions. And remember we talked about in chapter 2 about what holds the nucleus together, right? Like, for example, fluorine. You know, fluorine has 9 protons and 9 neutrons, or 10 neutrons. So what is it? Fluorine has 9 protons and 10 neutrons. 10 neutrons. What holds the 9 protons together? The nuclear force. And so do you guys remember talking about did I talk about the mass defect?
Yeah.
Okay. You guys remember the mass defect? Yes? No? You don't remember mass defect? Well, basically the quantities of energy involved in nuclear reactions is orders of magnitude larger than chemical reactions. And so even with something with an extremely high reduction potential, something that could potentially be very dangerous in high concentrations, isn't so significant to a nuclear chemist. Because the quantities of energy are kind of minimal. And so when we're looking at the stability of the nucleus, we want to look at what? When you're looking at properties, we always look for what? Structure and composition, right? And so we know the composition of the nucleus. That's easy. The composition is, it consists of what? Protons and neutrons, right? Composition is easy. And so we probably can correlate the composition based on the structure. So if something had 10 protons versus something that has 20 protons, is the thing with 20 protons more stable, less stable? Can you tell me? So for example, can you tell me which of these nuclei are most stable? Well, I know a lot of these aren't stable, like uranium. Uranium's not stable. Well, what would we do? You know, the scientific method is what? I just asked you a question. You know, this is, I have a little pet peeve because every time I ask about the scientific method, somebody always comes up with this, and they say that first you form a hypothesis, and then you ask a question. Well, my question is, or you test it. You test your hypothesis. Now, my hypothesis is what? My hypothesis is, tell me why something's radioactive and why something is not radioactive based on the composition of the nucleus, and let's test it, okay? And so why don't you come up with a question right now so that we can test it? Well, you probably could come up with a question. You'd say, 10 protons is stable and 20 protons is, or maybe I shouldn't say that. Maybe I should say from 1 to from 1 to 83 protons is stable. Okay? From 1 to 83 protons is stable, but from 84, remember polonium? Polonium is 84. Starting with 84, it becomes radioactive. Let's test it. Well, my test is here. I see that. It looks like polonium's radioactive, actinium's radioactive, radon's radioactive, francium, radioactive, radon's, actually, radium's radioactive, right? Not radon, radium, etc. So what have I just learned from that? Well, this is the reason, you know, if we want to really learn more about the stability, you know, the properties of the nucleus, then we got to look at the composition and the structure. And what we do is, when we're looking at the composition and structure, we're just looking for patterns, right? That's all we do. We look for patterns. Do you know how we can tell how stable a nucleus is? How we can tell how stable? How can we tell? Well, obviously, if it's radioactive, then it's not very stable, right? If it's radioactive, definitely not stable. But how can you tell when something's radioactive? Because, you know, carbon-14. Carbon-14 just screwed up everything for me because carbon-14 has less than 84 protons, and it's radioactive. P32, a whole bunch of other radioactive isotopes that have less than 83 protons. And so there must be more to it than that. So what's the next hypothesis that I'm going to develop? Well, I think I'm approaching it backwards. You know, when I have to come up with the theory before the observations, then that's tough to do, right? And so science isn't that complicated. Science is a lot easier because science, you just look at the patterns in nature and try to make sense of the patterns in nature, right? And so here, how can you tell, how does one determine the stability? Of the nucleus? Do you know how to weigh an atom? This goes back to chapter 2. How can you weigh an atom? Is it possible? No, an atom's too small to put on the balance, right? Balances aren't sensitive on it. We can weigh single atoms by using a mass spectrometer, right? But there's a much easier way to determine the mass of an atom, isn't it? The much easier way of determining the mass of the atom, true or false, is just add up the number of protons, number of neutrons, and number of electrons in the atom. And so if you have carbon 12 is easy. 6 protons plus 6 neutrons plus 6 electrons. I know the masses of these because it's in the book. The mass of a proton is in chapter 2, the mass of neutrons in chapter 2, and the mass of electron is in chapter 2, right? Just add up those masses and combine it. And so if I take the individual masses here and just sum up the masses, I'll get the mass of the isotope. True or false? That's false because the mass defect. Does it ring a bell, mass defect? It doesn't work, right? It doesn't work because what did we say about the mass defect? What is the origin of the mass defect? Mass is converted into energy, and that energy we call the nuclear binding energy. And so that's our secret. How does one determine the stability of the nucleus? Well, we figure out, or we calculate, the